welcome back as we talk about electrode current. So this is specifically concerned with kinetics and mass transfer. So there's two kinds of current that we need to worry about. There's Faraday current, which is current that results from an exchange of electrons across the electrode-electrolyte interface. And there's non-Faraday current, things like adsorption, desorption, or double layer charging. So if you remember back from the last lecture on thermodynamics, the potential drives reactions. And we often talk about this in terms of overpotential, where if your electrode is more negative than the equilibrium, then you have a negative overpotential. If your potential is more positive than the equilibrium potential, then you have a positive overpotential. And you can note here that you can describe the potential of your cell as the difference between your cathode and your anode, and your potential of your electrode in terms of your equilibrium plus an overpotential. Now, if you note, there's this IR term on both of these equations, and that refers to the potential drop that occurs because of the resistance in your solution. So your resistance in your solution multiplied by the current you're passing through that solution, that creates a voltage drop. So here's the current over potential curve, which is quite famous. This helps us describe what kind of currents will we see given a certain over potential. Here in the central region, this is the kinetically controlled region. This is where the factor that's limiting the current that we see is based off of kinetics. And you'll see that there's a very drastic increase between the potential that we apply and the current that we see. In fact, this is an exponential relationship if we're considering all other things equally. But once you start considering mass transfer, well, then this exponential growth becomes limited because you can only react materials as quickly as they're transferred to your electrode. And so whether you have a positive overpotential or a negative overpotential, you could have mass transfer limited current. Now, this is assuming that your reactants, in both cases, whether that's a reduction or an oxidation, it's assuming that your reactants and products are soluble in this case. So some factors that might affect your reaction rates. Of course, the first is mass transfer. So how quickly is your analyte reaching your electrode? The second is the electron transfer at the electrode surface. You can think of this in terms of electrocatalysis. So electrochemical reactions may occur more favorably on some substrates than others. For example, platinum is a very popular electrocatalyst that's used. The next is chemical reactions preceding or following the electron transfer. And then you might have other things like adsorption, desorption, or nucleation that could affect your reaction rates. So here's a little example of this is a reaction that's occurring on the surface of your electrode. We'd call this an inner sphere reaction. So you have your analyte, it diffuses randomly through the bulk of your solution, adsorbs onto your electrode. You have electron transfer steps, then it desorbs and diffuses away. And any one of these steps might be slower than another. It could become a rate limiting step. Now, of course, this is a rather complicated mechanism. Many mechanisms in electrochemistry, you'd only see the diffusion near the electrode. You'd have an electron transfer without adsorption or desorption, and then diffusion away. So how do we think about mass transfer in electrochemistry? We think about it in three terms: diffusion, migration, and convection. Diffusion is how species move based on a concentration gradient. Migration is how charged particles move under electric fields, which we of course have because we're applying potentials. So with migration, we might see a negative ion being attracted to the anode, which is positively charged. And then of course there's convection, where the fluid itself is moving, not just the species inside of it. So we want to define the diffusion layer. The diffusion layer is the region of your cell, your solution, where the concentration has been changed away from the bulk concentration. And an approximation that we usually use is we draw a tangent line from the concentration gradient curve, and then where that intersects the bulk concentration level, we say that's the diffusion layer thickness. Of course, it's just an approximation. We define the limiting current in terms of this diffusion layer. So here we have the current, it's equal to N, which is the number of electrons exchanged in our reaction, F, which is the charge per mole of electrons, HC, that's our mass transfer coefficient, the area of our electrode, and then the difference in concentration between the concentration at the surface of our electrode and the bulk. Now we can split up this mass transfer coefficient into diffusivity and a diffusion layer thickness, which then if you look at, you can then transform this whole reaction or this whole equation into NFA and then this term, negative diffusion coefficient times the change in concentration over the change in distance, which you can see here's the change in concentration, and then here's the distance that we're changing that concentration over. And this term is the flux. So this is the flux of our reaction. You can see this is what defines our limiting reaction when the concentration at the surface becomes zero. So that is the definition of mass transfer control, is when kinetics can no longer give us any advantage because it's already maxed itself out. We're already at the surface of the electrode. We've already reacted everything that we can. And so from this point on, we just have to rely on mass transfer to speed up our reaction. So if we look at, again, here's kinetic controlled. In this case, the concentration at the surface of the electrode is not zero. But once it reaches zero, then we become limited by mass transfer. How could we increase rates? Well, we could increase the limiting current here by stirring, by flowing our solution, things like that. So here's the question that I want you guys to answer before you move on to the next video. First, what's the defining conditions for the mass transfer limited regime? And second, are moderate or extreme overpotentials correlated with mass transfer limited behavior? So go ahead and pause the video. I'll give you a few seconds and then I'll give the answer. Okay. So the defining condition for mass transfer limited regimes is when the concentration at zero or zero distance right at the electrode is equal to zero. So in this case, kinetics has taken us as far as it can go. You can't have less than zero reactant at your electrode. And so that means that now we're just relying on how quickly can we bring the analyte to the electrode. And then if you think back on the overpotential curve, you can remember that mass transfer limited behavior, these plateaus, they occur at the extremes. Okay, so I hope you'll join us for our next and final video in this lesson, which is on resistance and capacitance.